Hello, everyone. Thank you for coming to this talk. I'm Sharat Ibrahimpur, and today I'll be giving a talk on our paper titled Approximation Algorithms for Flexible Graph Connectivity. This is joint work with Cheriyan, who is also at U Waterloo, Sylvia Boyd from U Ottawa, and Arash Haddadan from Warner Music Group. Most of this work was then done when Arash was a postdoc at U Waterloo. So what is flexible graph connectivity? It's a non-uniform model of survivable network design introduced by Ajishvili, Hamelsheim, and Mullen-Taylor. In an instance of FGC, we are given an undirected multigraph G on n vertices and n edges. Edges have non-negative cost, and the edge set is partitioned into two parts, safe edges and unsafe edges. A key property of safe edges is that they never fail. In the figure here, I've drawn an instance of FGC. So what is the goal in FGC? We want to find a minimum cost subgraph F such that V, F is connected no matter which unsafe edge is deleted. So this is going back to this figure. I've represented safe edges by using solid green edges and unsafe edges by using dashed red edges. I've drawn two possible FGC solutions. This list is not exhaustive, of course. This solution is feasible because no matter which unsafe edge you delete, the remaining subgraph is still connected. And this subgraph is feasible for FGC because there are no unsafe edges in this, so there is no chance of losing connectivity. Again, I would like to make a remark that in all the problems that we considered in this work, we may pick at most one copy of an edge. What are some special cases of FGC? Okay. Consider the case when all edges are safe. Then FGC reduces to the minimum spanning tree problem. On the other hand, when all edges are unsafe, FGC reduces to the minimum cost two-edge connected spanning subgraph problem. So in some sense, FGC interpolates between one-edge connectivity and two-edge connectivity. Here's a characterization of FGC solutions. And it said F is feasible for FGC if and only if in every cut S, delta S intersect F contains a safe edge or two edges. Here, delta S denotes the set of edges with one endpoint in S and one endpoint not in S. Now I'll describe two possible generalizations of the FGC model. Consider a parameter, integer parameter P, which will denote the connectivity requirement. We are given an instance of FGC. And now in the P, 1 FGC problem, we want to find a minimum cost F such that the subgraph V, F remains P edge connected against failure of any one unsafe edge. Again, a subgraph V, F is feasible for P, 1 FGC if and only if for every cut the subgraph contains P safe edges or some P plus 1 edges. They may be safe or unsafe, some combination of those. So P, 1 FGC can be seen as an interpolation between P edge connectivity and P plus 1 edge connectivity. We can also generalize the robustness parameter in FGC. Let Q be a non-negative integer parameter, which denotes the number of unsafe edges that can fail. Yeah. So the goal in 1, Q FGC is to find a min cost subgraph that remains connected against failure of any set of at most Q unsafe edges. I'd like to remark that this model was proposed by Ajishvili et al. In their IFCO paper. So here's a result, helpful claim. F is feasible for 1, Q FGC if and only if for every cut, the subgraph contains a safe edge or Q plus 1 edges. And we could combine these two generalizations to form one very general model, which we'll call like P, Q FGC. Here, P and Q are two integer parameters. And the goal in P, Q FGC is to find a minimum cost subgraph that remains P edge connected against failure of any set of Q unsafe edges. Again, it's like, as we have seen before, like a subgraph is feasible for PQ FGC if and only if the subgraph contains P safe edges or P plus Q edges on any cut. Right. There is another problem which models non-uniformity in survivable network design called as capacitated K-edge connected spanning subgraph problem. This problem has like close connections to FGC. Okay? This model was introduced by Gomez et al. In the 90s. Capacitated K-ECSS is simply the capacitated version of the well-known K-ECSS problem. Here we have a multigraph G and a positive integer K. Here K specifies the connectivity requirement. Each edge E has a non-negative cost CE and a positive integer capacity UE. It's helpful to think of UE as some sort of a safety rating of edge E. The goal in capacitated K-ECSS is to find a min cost subgraph F such that for every cut, the capacity of that cut in the subgraph is at least K. So in some sense, we are asking for like a safety rating of at least K on each cut. Again, I've drawn a figure in case you need like more clarification with the definition. I'd like to remark that buying an edge E costs CE and gives capacity UE. Fractional buys are not allowed, and at most one copy of an edge can be bought. Now, what are the connections between PQFGC and capacitated K-ECSS? If P equals 1 or Q is at most 1, then PQFGC is a special case of capacitated K-ECSS problem with K equal to P times P plus Q, and safe edges having a capacity of P plus Q, and unsafe edges having a capacity of P. To see this, I'll just consider the case of basic FGC, which is 1,1 FGC. So the instance of capacitated K-ECSS that's generated has K equal to 2. So we have capacitated 2 ECSS instance, where safe edges have capacity 2 and unsafe edges have capacity 1. Now, if on any cut we have capacity at least 2, because that is the value of K, then it is easy to see that either we must have a safe edge in that cut, or we must have like 2 unsafe edges. So in either case, we see that like this is the property that we needed for basic FGC. A similar argument shows that P, 1 FGC and 1, Q FGC can also be cast as special cases of the capacitated K-ECSS problem. So what can we say about like general versions of PQFGC and capacitated K-ECSS? In general, they might be incomparable. In particular, I'll give an example showing that PQFGC is not the same as Cap-k-ECSS, with K defined to be set to be P times P plus Q, safe edges having a capacity of P plus Q, and unsafe edges having a capacity of P. Concretely, fix P equal to 2 and Q equal to 2. Then K equals 8, and safe edges have a capacity of 4, unsafe edges have a capacity of 2. Consider a solution F and a cut S such that if you look at the edge set, the set of F edges on this cut, and let's say if this edge set has 1 safe edge and 2 unsafe edges, exactly this. Okay? In the PQ-FGC model, this cut certifies that F is infeasible because Q equal to 2. So if these two unsafe edges were to fail, then you only have one safe edge remaining. But we needed like at least two edges to survive, no matter like which two unsafe edges fail. So that's why like there is like infeasibility in the PQ-FGC model. However, in the Cap-k-ECSS model, the cut has capacity 8, 4 plus 2 times 2. So this is not deficient in that model. So in general, like these two models can have like different sets of feasible solutions. Now let me get to our results, our main results. Yeah. On this slide, I'll mention like our results on weighted versions of the problem. So all edge costs are arbitrary non-negative numbers. I'll use a Venn diagram to show the entire collection of our results. And I'd also like to remark that all our algorithms are deterministic. For the most basic version of FGC, that is 1,1 FGC, we give a 2 approximation algorithm. This improves upon Ajishvili et al.'s 2.527 approximation and matches the best known approximation ratio for the 2 ECSS problem. For the more general 1, QFGC problem, where we want connectivity against failure of Q unsafe edges, we give a Q+1 approximation algorithm. For the complementary problem, where we want pH connectivity against failure of one unsafe edge, we give a 4 approximation algorithm. For the model that combines these two aspects, that is PQ-FGC, here we give a order Q log n approximation. Lastly, for the capacitated k-ECSS model, which generalizes these 3 models, we give an approximation algorithm whose ratio is the best of k, the connectivity parameter, and twice of the maximum edge capacity. Here, like there is some prior work on capacitated k-ECSS. Gomez et al. In their work, they gave an approximation algorithm with ratio min of 2k and m. Observe that our algorithm has better dependence on k. In the last decade, Chakrabarty et al. Gave a randomized order log n approximation for this problem. Observe that like our result is incomparable to the result of Chakrabarty et al. Our result is independent, the approximation guarantee is independent of the size of the graph, whereas Chakrabarty et al.'s approximation ratio is independent of the connectivity parameter k and the edge capacities UV. On this slide, like I'll mention a result on unweighted 1, 1 FGC. In the unweighted version, the cost of all edges is the same. Let's just assume it's 1. Here we give a 1.455 approximation algorithm, which improves upon Ajishvili et al.'s 5/3 approximation algorithm. In the interest of time, we do not go into the details of this algorithm or its analysis. Before getting into the proof techniques, let me give a very high-level overview of what techniques we use in proving our results. So for these 3 problems on the right, that is 1, 1 FGC, 1, QFGC, and capacitated k-ECSS, we give a single algorithm based on a reduction to the minimum cost rooted k arborescence problem for an appropriate choice of k. On the other hand, for P, 1 FGC and P, Q FGC, we'll give a 2-stage algorithm, where in the first stage, we'll compute a partial solution F that is mostly feasible. That is, there are at most polynomially many cuts that are deficient. In the second stage, will repeatedly augment F until all deficient cuts are fixed. We'll now give the technical details of these algorithms. Okay. To understand our arborescence-based algorithms, it is helpful to give like a gentle introduction on arborescence. Consider a directed graph D on n vertices. Let's designate a vertex R in this diagram as the root vertex. Let me define what an arborescence is. A subgraph of D is called an arborescence if it satisfies the following two conditions. The undirected version of the arborescence is acyclic. And two, for every vertex in the diagram, there is a directed path from R to that vertex. On the right, I've drawn a figure of an arborescence. Intuitively, like if you want to imagine an arborescence, think of a spanning tree where all the arcs are pointed away from the root. That's what arborescences look like. More generally, a K arborescence is defined as a union of K many arc disjoint rooted arborescences, where all arborescences share the same root vertex. Here is an observation that will like come in handy in a few slides. Fix a rooted K arborescence and consider any two vertices X and Y. Then the number of arcs in this K arborescence with endpoints X and Y is at most K. So this will be a result. This follows from the property that arborescences are acyclic and that K arborescences are union of K arborescences. K many arborescences. On this slide, I'll mention like two results on rooted K arborescences, which again we use in our algorithms and analysis. The first theorem is a necessary and sufficient condition for the existence of a rooted K arborescence in a digraph B. What this says is, if for every cut that excludes the root vertex, we have that the number of incoming arcs is at least K, then we are guaranteed the existence of a rooted K arborescence in B. And this condition is both necessary and sufficient. Let CA be some arbitrary non-negative cost on the arcs of B. Here is an optimization problem. And this theorem basically gives us an optimal solution to finding a minimum cost rooted K arborescence. So in time polynomial in N and K, we can obtain an optimal solution to the minimum cost rooted K arborescence problem on B, or conclude that there is no K arborescence in B. Now I'll describe the actual algorithm that we use for 1,1 FGC. To make it like I'm going to present the entire like algorithm and its analysis using pictures. So let's say we are given an instance of FGC, which is shown here. Recall that I use solid green edges to denote safe edges, and I use dashed red edges to denote unsafe edges. The labels represent the cost of that edge. So given an instance, we'll construct an auxiliary diagram. How do we do this? We are going to bidirect each unsafe edge once. We take this edge, we introduce two arcs, one going from this vertex to this vertex and the other going in the opposite direction. And for safe edges, we'll bidirect this safe edge twice, okay, as you can see here. Okay. And the cost of all these arcs will be the same as the edge that gave rise to it. Next, we'll compute an optimal two arborescence rooted at some root vertex, some arbitrary root vertex in this diagram. Let's just pretend that I have the two arborescence that I've drawn here as an optimal two arborescence. Okay. Why is this two arborescence? I've drawn an arborescence in pink and I've drawn an arborescence in brown. Okay. And as these are arc disjoint, the union of these two arc sets is a rooted two arborescence. Next, how can we infer a FGC solution from this? By simply like forgetting orientations of the arcs and retaining at most one copy of each edge. Okay. This gives us the solution which is highlighted here. Why is this a feasible FGC solution? Simply because we know that for any cut in this diagram, there are at least two incoming arcs, simply because that's the property of a two arborescence. We had a necessary and sufficient condition on a previous slide. Okay, so consider any cut here, and if you go back to the same cut here, if there was a safe arc entering that cut, then it means in the undirected version, you'll have a safe edge. If that does not happen, then I claim that there must be at least two unsafe arcs entering that cut. And why does this happen? Because observe that for each unsafe edge, we only bidirected it once, which means that the two incoming unsafe arcs couldn't have originated from the same unsafe edge. So we have like two distinct unsafe edges, which contribute two unsafe arcs entering a cut. So overall, like this shows that the solution we obtained from this algorithm is feasible for FGC. Now let's analyze this algorithm. Again, I'll use pictures. Consider an optimal FGC solution at star, which is shown here. Let's restrict to this optimal solution. We'll again build an auxiliary digraph by bidirecting safe edges twice and bidirecting unsafe edges once. So we get this digraph. Now in this digraph D, we'll consider a minimum cost rooted two arborescence. So first question should be, why should a two arborescence exist in D? Okay. Again, recall that a two arborescence exists if we can show that the number of incoming arcs in any cut is at least two. Okay. Why is this the case? Okay. Let's consider an arbitrary cut here. Why should this cut have two incoming arcs? Let's go look at this cut in the original instance. Look, there is a safe edge on this cut because we started with a feasible FGC solution. So if we look at this, because safe edges were bidirected twice, we'll have like two incoming arcs entering this cut. On the other hand, if you consider some other cut, why should this one have two incoming arcs? Let's go to the corresponding cut in the original instance. Again, by FGC feasibility, we have two unsafe edges on this cut. So each of these will contribute one arc to this cut. Okay. So this shows that a two arborescence exists in this diagram. Okay, next, let's do the cost analysis. Observe that we created 4 arcs per safe edge. So shouldn't the calculation have like a multiplier of 4 for the cost of safe edges in an optimal solution and a multiplier of 2 for the cost of unsafe edges in an optimal solution, thereby yielding a 4 approximation. So how do we get like a 2 approximation? Recall something that I mentioned earlier, that for any 2 vertices in this diagram, a k arborescence uses at most k arcs with endpoints x and y. So if we do this calculation now by using this property, we'll get the required 2 approximation. Okay. Let me also talk about like extensions of arborescence-based algorithm to 1, Q FGC and capacitated k-ECSS. Our extension here pretty much goes like super smoothly. There is like nothing extra that needs to be done. The auxiliary diagraph that we construct will have q plus 1 bidirected arcs for every safe edge. And for unsafe edges, we only bidirect once. Yeah, and we'll compute a minimum cost q plus 1 arborescence in D. And the undirected version of this arborescence will give us a feasible solution to the 1, q FGC problem and has an approximation ratio of q plus 1. And for the capacitated KCSS problem, the auxiliary diagraph that we construct will have UE many, the capacity many copies of bidirected arcs for each edge E. And we'll compute a minimum cost K arborescence in this auxiliary diagraph. And the undirected version of this K arborescence will give us a feasible solution for capacitated KECSS problem. And the solution is a K approximation. Furthermore, the same solution also satisfies the approximation guarantee of 2 times the maximum edge capacity. This is simply because an edge E gives rise to at most 2 times UE many arcs. This is simply by the way the diagraph was constructed. So overall, like we get an approximation ratio, which is the better of these 2 terms. Okay. Now let me focus on 2-stage algorithms for P,1 FGC and PQ FGC. Recall again that like we want pH connectivity against failure of any one unsafe edge. So what we do here is in the first stage, we'll ignore safe, unsafe labels and simply compute a 2 approximate pH connected spanning subgraph solution in the given graph G with the given cost C. Since the optimal subgraph V, F star is already pH connected, the cost of F is at most twice of opt. Now let's ask ourselves what makes the solution F infeasible for P,1 FGC. So the problematic cuts are basically those cuts where the size of the cut is exactly P, that is, it is a minimum cut in the subgraph V, F, and it is the case that delta S intersect F contains an unsafe edge. So if this edge fails, then we have a cut where we only have P minus 1 edges. So these are the kind of cuts that are problematic, and we'll call them deficient. In the second stage, we'll fix these deficient cuts. How do we do this? We consider the collection of all deficient cuts. To fix F, observe that it suffices to include a single edge for each of these deficient cuts. And it doesn't matter whether this edge that we include is safe or unsafe. It's just a hitting set problem now. The key observation in our work is that this collection script C forms an uncrossable family of cuts. Using the machinery from Williamson et al.'s work, we get a 2 approximation algorithm for this hitting set problem on an uncrossable family. This shows that the cost of augmentation is within 2 times opt. Overall, this gives us the desired 4 approximation. This is the last technical slide. Here I'll talk about the 2-stage algorithm for P, Q FGC. Okay. I'm going to assume that P is strictly less than Q, simply because this is the harder case. P at least Q is easier to handle. In the first stage of this algorithm, we'll construct an instance of capacitated KECSS problem with K equal to P times P plus Q. We'll assign a capacity of P plus Q to safe edges and P to unsafe edges. Again, recall that in the first half of the talk, I mentioned that PQ FGC and Cap-k-ECSS are not comparable. But it turns out that this particular instance gives us a partially feasible solution for the P, Q FGC problem. Okay, so why does that work? I'll explain it now. Okay. So using our capacitated K-ECSS algorithm on the above instance, we can obtain a solution F such that the capacity of any cut is at least K. So the expression for the capacity of any cut has the following form. Observe that every edge contributes capacity P. So we get this term. And every safe edge additionally contributes a capacity of Q. So we get this expression for the capacity of a cut. And by the approximation ratio of our algorithm, we know that the cost of F is at most 2 times the largest capacity in this instance, which is P plus Q. So overall, this is the approximation. This is an upper bound on the cost of F. Now, it might happen that the solution F is infeasible for P, Q FGC. So what causes infeasibility? Let's see. So let's assume that there is a cut S, which is deficient with respect to F. Then I claim that the capacity of that cut is at most 2K. So it is a near minimum cut in this capacitated graph. Okay, why is this the case? By definition, since S is deficient, it must be the case that there are fewer than P edges in that cut, say fewer than P safe edges in that cut, and fewer than P plus Q edges in total in that cut. So this gives us the bound that the capacity of a deficient cut is strictly less than PQ plus K. Okay. Now, in the second stage, we'll fix these deficient cuts. How do we do this? We'll first enumerate all deficient cuts. Because they're near minimum cuts, this can be done deterministically in polynomial time. We'll repeatedly augment F until all deficient cuts are fixed. To do this, we use a black box hitting set algorithm. We incur an approximation loss of order log n in each step. Overall, there are at most Q augmentations. Why is this the case? Observe that every deficient cut starts with a capacity of at least K, and it stops being deficient once it reaches a capacity of PQ plus K. And because each augmentation gives us an additional capacity of at least P, there can be at most Q augmentations. Overall, this gives us a Q log n approximation. Okay. I'll now conclude the talk with by mentioning a few open problems. On the previous slide, we saw Q log n approximation for P, Q FGC. It would be nice if we can remove the dependence on log n and give an approximation ratio that is independent of the graph size. Next, can we do something better for the case when Q is a constant? Okay. So is there a constant factor approximation for P, 2 FGC? The problem is open even when P equal to 2. That is, we don't know of a constant factor approximation for 2, 2 FGC. Next, we gave a Q plus 1 approximation algorithm for 1, Q FGC. Can we obtain a little OQ approximation for this problem? Or maybe show that this is impossible, like through a hardness result of omega Q. Lastly, can we improve the approximation ratios for P, 1 FGC and unweighted FGC? Our current ratios are 4 and 16/11. And can we improve on these ratios? With this, I would like to end my talk. Thank you for your interest in our work.